Kia ora koutou katoa, it's Mrs. Goodson here, and this is lesson 12 for level 1 science, genetic variation. And in this video we're going to cover pedigree charts or family trees. And pedigree charts show the actual phenotypes, actual observable traits. And we're just remembering that we, because it's only level 1 science and we're just learning about genetic variation and inheritance, that we are just going to keep it simple and look at monohybrid crosses and simple inheritance. So we are going to interpret pedigree charts or family trees to identify patterns of inheritance, explain patterns of inheritance for simple single gene inheritance using pedigree charts, including genotype and phenotype ratios. Okay, so what are pedigree charts? A pedigree chart shows a genetic family tree for the inheritance of a trait. It shows the phenotypes of individuals from several generations, and it is used to determine the dominant and recessive alleles. So we're trying to work out genotype. It gives us the phenotypes, it gives us the actual, compared with the Punnett squares that we looked at in another video that give us the probability, the expected ratios, the expected outcomes. This gives us the actual outcomes over several generations so that we can work out the genotypes of individuals. Now this pedigree chart shows the inheritance of having 6 toes on their feet. All right, so we use a square for males, we use a circle for females. There'll always be a key, so you're going to need to look out for the key which explains the symbols. And in this case, normal means they've got 5 toes, and affected means that they have 6 toes. So the little black square and the little black circle means that they are affected, they've got 6 toes, and the uncolored in ones are normal. Okay, so we've got several generations. We've got individual 1 and individual 2. So we've got a female and a male, and they have one child, which is number 3, which is a female who is normal. And then they are the lines they mated with or had offspring with individual 4, and their children are number 5, number 7, and number 9, and their children are this next generation here. So we've actually got 4 generations in this family tree in this pedigree chart. Okay, so we're going to use this to work out the genotypes of different individuals. The first thing we want to know is it a dominant or a recessive trait? Looking at the chart is easy to assume that the 6 toes because it is less common, but you must be able to explain this and examine the genetic relationships between the parents and the offspring. So if you have a look at the first generation, which is 1 and 2 up here, so we've got the first generation, they produce one child, number 3, okay, which was normal. Individual number 3 has 5 toes. Okay, so since she had parents with 5 and 6 toes, so number 1 had 6 toes affected, number 2 had 5 toes normal. So number 3 must have got both genes. Since she has 5 toes, the 6-toed allele must be hidden and therefore recessive. So 5 toes equals dominant, big T. So we're going to put a big T for dominant, and recessive is a little t. So individual 3 must be heterozygous, be a big T, little t. So what we're going to do is, as we go through the chart, we're going to write all over it. So we've worked out which one is dominant, which one is recessive. So 5 toes is dominant, 6 toes is recessive. So we know any individual that has the recessive phenotype that we observe, we're going to put 2 little t's next to them. So grab the pen here. So 2 little t's, number 1 must be 2 little t's, because that means they don't have the dominant allele. Okay, so as you go through, you start to work out the genotype of the individuals. Okay, so you can see that number 3 must have got a little t from parent individual number 1, and because they are normal, they've got 5 toes, you must have a big T as well. So number 3 must be heterozygous. Okay, so genotype of individual 4. Okay, so we don't have individual 4's parents, all right? So we've got to look at their offspring. He is a male because he's a little square on the pedigree chart. He must carry the dominant allele because he's normal. Okay, so right, dominant allele straight off there. He's produced an affected child. So we look at the children. So the children are number 5, number 7, and number 10. Sorry. I think I said 9 before. It's 10. Look carefully at those lines. But number 5 is 2 little t's because they have the recessive phenotype. So that means that they must have got a little t from both parents. So both, we already worked out 3, but 3 and 4 must be heterozygous because that is the only way that they could have produced a child with that is homozygous recessive. Okay, so we've worked out the genotype for individual 4 because he's got the dominant allele because he's showing the dominant phenotype, but he's also carrying the recessive allele because he's got offspring that is homozygous recessive. Male 5 has to inherit 1 6-toed allele from each parent, and both parents are normal, so both parents must be heterozygous. What is the genotype of individual 6? Okay, so again, we don't have the parents of individual 6 because they are the partner of number 5, but we know number 5 is 2 little t's, homozygous recessive. And so if you look at their offspring, they are both normal, so they both must have 1 copy of the dominant allele. And because they we know that they both must carry the recessive allele because they've inherited it from number 5. So we know the offspring are both 11 and 12 are both heterozygous, but we actually don't know. We can't work out whether number 6 is 2 big T's or big T, little t. We know that they've got 1 copy of the dominant allele, but we don't know whether they have 2 copies because it could. They've only had 2 children, so unless they have another child that has 6 toes, then we cannot know. We can't work out. We don't have enough information to work out whether number 6 has 2 big T's or big T, little t. So we can't work it out completely, everyone's genotype. We would need more information, and one way is if they had another child, and if the child had 5 toes and was dominant, we still wouldn't know for sure. The more children they have, the more likely we could be sure. But we can only definitely work out that 5 has 2 little t's and 11 and 12 are heterozygous. So here is an example for you to work at. You might want to pause the video and have a look at this. This is my family. So I am right-handed. So I must have, we're going to use R for right-handed. R is dominant. Right-handedness is dominant. And my husband is also right-handed, so he must have a copy of the big R. Now, my children are Leo and Ellie, and Leo is left-handed, which is recessive, so he's got a genotype of 2 little r's. We're not sure about Ellie. She might be 2 big r's or big R, little r. So we both have this right-handed gene, but we've got a child that has a different. So that confirms the left-handedness is recessive, right? And the reason that Leo is left-handed is because that means we both must carry the left-handed gene. And now it turns out that we got that from our parents. So Mark got it from his mum, Lorna, and I got it from my dad, Mick, over here. So they are both left-handed, and so they have passed those genes on to us. And so both parents must carry the recessive allele to work out. So both myself and Mr. Goodson are heterozygous for left-handedness. And you might want to draw a Punnett square to remind yourself how that works when you have two heterozygous parents, how they can produce a homozygous recessive child. So this video has been about interpreting pedigree charts, what pedigree charts are, and using them to explain patterns of inheritance and to work out genotype of different individuals, work out whether a trait is dominant or recessive. And the best way to continue to learn about pedigree charts is to do examples and previous exam questions. Do lots of examples about pedigree charts and how they work.